Welcome everyone to Deeper Enforcement Learning and Control. We have a very exciting lecture for you today. We will continue on the wonderful paper we started last time, comparing offline Monte Carlo research versus online reinforcement learning with deep Q networks. And we'll move to our next chapter, which is policy gradients. How can we learn policy networks with trial and error learning? We don't have any logistics to catch up with. Homework 1 is due on the 26th. You may want to start reading for your quiz 1, simply because quiz 1 is, the terminology, we introduce a terminology. This is super important to get right, to be able to, feel comfortable for the rest of the course. Are there any questions from you? Yes?
Do we know what will happen in the recitation on Friday and next Friday? Is there a handout plan?
Yeah, so the recitation, guys, is for you. The recitation is, there's no specific ones for recitation. The ideas for recitation is you to send the ideas to the TAs and say, look, I really want this topic to be covered or that other topic to be covered. So it's actually an hour for you to use the TAs in a more structured way. So I really would encourage you to send, Piazza posts about the recitation. We can also have a specific channel about recitation formation on Piazza. Otherwise, if you don't, proactively guide the TAs of what to cover, we're just going to cover concepts from the course or background material about neural architectures and so on. Yes?
One more follow-up on the quiz. I think just one day before the quiz on the Wednesday, we covered TRPO, PPO, and everything.
Yeah.
That be part of the quiz?
So when is the quiz? I think it's October 6th or
October 7th. And October 5th, we will materials. I'm trying to...
Yeah, no. So the material that we will use for our quiz will end coming week, at the end of coming week. Now, the truth is that TRPO will be covered on Wednesday coming week, based on the updated website, if you go and check. Okay. So, but that's it. On the same week of the quiz, this material will not count towards the recitation. Now, if you're also very, excited about it and you have opinions, we can also remove the natural policy gradients, no problem, and we can just push that topic to the second quiz. That's totally, actually, maybe we should do that. And you will know from now that everything up to policy gradients, which will cover this lecture and next lecture on Monday, will be part of quiz 1. And from natural policy gradients and onwards, will be part of quiz 2. Okay, is that so? Now you have plenty of time to sync the concepts and so on. Yeah. Other questions? But this is a great question. Yeah. Thanks for asking the question. Other questions? Okay. So let's jump to this wonderful paper. Why this paper is wonderful? Because for many people, many people, the idea of planning versus training with trial and error learning are, kind of confused. All right. And this paper simply makes the very simple statement that if you give enough resources to a planning method, and this planning method has access to the true dynamics and reward functions, it will come up with very, very good Q estimates, which means expected rewards from a particular state and action. And you can use those Q estimates to act greedily over them, and that's it. And because this planning process is very slow, what you're going to do is you're going to use the planning process to give you the ground truth Q values. I mean, it's not, of course, ground truth, it's approximate, but they're good approximations. That's the idea. Much better approximations that the deep Q learning approximations does to the Q state action value functions. And then distill those to a policy, a classifier network, okay, which is a policy of given the particular state, which action should I do? Okay, the action, of course, that has the highest Q, or a regression network, given this state and action, what's the corresponding value? And we'll see the difference between the two. This is the main thesis underlying the paper, okay? All right, that all we are after here in this course is good estimates of which actions are the best to try in a particular state. And a planning process with enough resources, trained offline, will give you good estimates for you to use. Does this make sense? Okay, of course, we're going to spend the whole chunk of the second part of the course talking about model-based reinforcement learning and planning and learning, but this is a very important paper to get right and to understand, its points. All right, any questions? Okay, so here's what they propose. They propose we're going to instantiate a Monte Carlo tree search agent that just plays against itself and generates tuples, state and action Q, and the Q value. And that state is the root of the tree. So that agent is going to, use a particular state, develop a whole tree, estimate the Q for all the actions of the root state, play, jump to the next state, do exactly the same thing for the next state, and so on. And once it plays a whole game, it has good estimates, good Q estimates for the states and action that it has visited. All right, that you can use as your annotations for training your value function or your policy, as we're going to see. And UCT to regression, and by the way, UCT is another way to refer to Monte Carlo tree search. So UCT to regression is that you're going to take these tuples of state, action, and Q values and train a regression network that takes as input the state and the action spits out the scalar, or takes as input the state and for every action spits out the corresponding scalar, right? And we have 18 actions. And UCT to classification means that you're just going to train a classifier that for a particular state, it assigns highest probability to the action with the highest Q. Does this make sense? So you will use the Qs of the actions, of the 18 actions, to come up with a ranking, and the action that has the highest Q is the one that your policy should be predicted. Is this crystal clear, what they are proposing to do? Okay. And does anybody remember why we are not going to use the Monte Carlo tree search planner to directly play the game? Why we need to go through the intermediate stage of training, essentially doing this distillation UCT values to a regression network or UCT to a classifier?
It's too slow for real time.
Yeah, I think they say that the planner plays one full game. It takes 2 days of CPU, single CPU core, etc. All right. By the way, playing one game means that for every state that you visit in the game, you need to, unroll tons of trajectories, make a big tree to have good estimates of your Qs at the root. All right. That's what means playing a game. So it's super slow, right? That's what you're saying. While if you train a regressor or a classifier, this is fast. Do you agree that every time step you just feed the state, see the action, play the action, and move on, correct? It can be real time. Okay, great. All right, so this was last time to remind you how Monte Carlo tree search works. I think the best way to understand this, guys, is you just do the homework exercise that will show up, homework 2 or 3. Okay, so the most important thing to remember is that there are 2 different policies in Monte Carlo tree search. One that you use within the tree, what they call tree, and the other that you use outside of the tree. Does anybody want to remind us what are the 2 policies within the tree and outside the tree? Yes?
Within the tree, it's like a random policy for expiration. And then you keep track of the values at each of the states you visit, and then you develop it on a larger scale.
And outside the tree?
Oh, sorry. I meant that for outside.
So outside is a random policy.
Inside's random.
Okay, and outside?
Outside, based on your random expiration inside the tree, you'd keep track of the different stage values.
Okay. Other ideas? Yes. Just to have multiple people talk. Okay. That's all. Yeah.
So outside the tree, we're doing a random just traversal to the end.
A random traversal just means that I sample actions randomly on the states that I visit. Okay, yeah.
And then inside the tree, we're we have constrained, going through the tree to sort of find, not going through options that we think are going to be bad at all. And then we sort of have that guided search until we get to
Mhm.
the end of the tree.
Yes. So your colleague says inside the tree is going to be more guided search and outside random. Other ideas to make the guided search more concrete?
Yeah, basically, use on the colleagues like opinions inside the tree, looking on Q, and use see with the looking Q to like the smart.
Yeah. So for a state and action to be within the tree means that state and action and all the other actions have been tried at least once. This makes that state and action within the tree. So when a state and action is within your tree, you have both a Q estimate for that, as well as this upper confidence bound, the second term that takes care of the exploration bonus. All right. So the only thing that you do inside the tree is you take capital Q plus C, a constant parameter, as well as this fraction, if you remember, the grad, square root of the log T, how many times you visit the parent node divided by NTA, how many times you have played that particular action. And that's it. That you just compute this for every state action within your tree, and you take the arm across actions, and that's how you play. Do you see? It's super concrete. All right. So I really want you to go and read this 8.11 chapter to see the details of that. But it's pretty much that's it. So there is a tree, there is something outside the tree. Each time I unroll a trajectory, my tree expands by a single node. Okay. And for that node, I make sure I first play each action at least once. And once I play every action at least once, then I use just the UCB criterion to select actions for that node as well. And that's how things continue. So I really hope you guys make this super concrete on your, just read about it, because we're going to ask questions on the quiz. And the reason is that we are going to see much more involved and interesting Monte Carlo tree searches in the future lecture, when we discuss about AlphaGo and AlphaGo 0, where this very simple search we just described will be combined with neural networks that guide action selection and guide value estimation. So we really want to understand those amazing algorithms well. So for this to happen, we want to understand the basic algorithm well. And we're going to do our part of adding this in the homework, okay? All right, so this is exactly what you guys said. So let's see now what we're going to do. So we're going to take that Monte Carlo tree search process as a black box, and we're going to use it to estimate Q values. And I asked this question last time, and you guys gave very good answers. You said, one of your colleagues brought up the issue of computation. How much budget will you give to the planner, and how much budget you will give to the DQN and so on. And the truth is that because the planning is a much more methodic search, it takes, it exploits resources in a much better way, right? Simply because the exploration is so methodic. So we'll give a lot of budget in our Monte Carlo tree search planner, and I'll show you also how much we can afford, at least how much they afforded in 2014 when this paper came out. We answered already this question that Monte Carlo tree search is too slow. Yeah. So this is their pseudocode basically. They said, they said, we're going to have an agent. He's going to play tons of games. We'll take the resulting tuples of state action queues, and we're either going to train a regressor or a classifier. And there is a problem with this method. There is a problem. And this problem is a big problem, which we're going to visit essentially when we talk about imitation learning. I'm not sure if you realize, but what these people suggest is simply to imitate a planner. Do you see? So you have a planner. He's not a human expert, okay? It's just a planning algorithm that can, use resources well and explore methodically. And this planner will come up with cues, and we're just going to imitate the cues, okay? Now, when you do imitation learning, as we're going to see actually this in like 2 weeks from now, when we jump to imitation learning, very nice and simple lectures, and again, things are going to get very easy for us, much easier than now. You will see that we're going to talk a lot about this distribution shift and so on, which means what? It means that doesn't suffice for me to learn well from my imitator, from my teacher. For my teacher, it's not suffice for me to imitate its actions in the states that the teacher visited. This doesn't suffice. Why? Because when I go to play, I'm going to make small mistakes, okay? So they're going to be small, but because these mistakes in the actions, I'll actually deploy them in the environment, and I will result on states that are slightly different than what the teacher had seen, then again, I'm going to play. Now the error is going to become even larger. I'm going to play it in the environment. Again, I'm going to result on a state that the teacher has not seen. And the further away I go from the state distribution of the expert, the bigger mistakes I'll make, and eventually I'll crash. Okay, so we will see that. This is a very old problem that, self-driving cars were, first self-driving car came out in 1980s in CMU. We will see either in that very old paper that there is a paragraph explaining why, just imitating actions of instantaneous time steps does not suffice. Because if you just imitate perfect expert, you do not know when an error shows up and you go close to the sidewalk or to grass and so on, how to correct yourself. You see, there are no correcting moves on those expert trajectories. Does this make sense? So this is the problem, and we'll come up with a lot of different methods of how to alleviate from this problem of distribution shift between the expert and the student. Okay. One very simple fix is this iteration, what we're going to call dagger, which means we take the data set of the expert, which is a set of tuples of state action queues. We train a policy or regression. Then we deploy the agent that actually use this policy to play games. And then we'll take the states that the agent visits to ask again the teacher, how did you play from there? And then collect a new data set from the teacher, which will aggregate with the previous data set, retrain the policy or the value function, have a new agent, the new policy, deploy it in the environment, see the new states that this agent visits, go back and ask again query essentially the teacher iteratively to ask him about actions on states that go beyond the initial data sets. Is that clear? So basically, there is this interleaving between I deploy the agent, it visits some states in the environment, I give the states to my Monte Carlo tree search planner, which is my expert. I ask the planner, in those states that I visited, which actions have the highest use? The planner replies by unrolling the trajectories. You take this new data, retrain, and so on and so forth. Is that clear? This is precisely what this says. Deploy the policy for 100 runs, and 5% of the time you also allow some random actions and so on. And then use the Monte Carlo search to decide which is the best actions from these states, essentially estimate the queues, and then you go back to 2, and so on. Are there any questions on this interleaving between annotating trajectories with best actions or Q values from the expert and then collecting trajectories? We will see this in great detail when we go to the imitation learning lecture. Yes?
Are 200 runs enough to train the UCT classification model?
Yeah, by 200 runs, every run is a whole game, right? Every run is a whole game from the beginning till the end.
A lot of frames.
Yeah, it's a lot of frames. Yeah, right. So I have a question for you. Would you, and the next slide will give us the answer, but before looking at the next slide, would you be able to guess what will it do better, UCT to regression or UCT to classification? If I give you tuples of the form state action and the scalar Q S comma alpha, which is the estimate of the expected sum of discounted rewards from that state and action onwards, do you think it makes more sense to train a regression network, like a real Q network, or do you think we should train a policy? The policy doesn't have a clue about the exact Q of every action. It only knows about the ranking, that this action is better in this state than the other actions. What do you think would make more sense? Yeah?
I think it's classification.
It
is playing a Atari, so the action space is discrete. So there's like finite amount of possibility for you to guess it right. But if you're doing regression, it's like a continuous value. So it will be like much tougher.
So your colleague says, okay, I have a discrete set of actions. This has always been the case so far in our lectures, right? Since the only thing I care to play the game is which action is better than the rest, Why should I, sweat my network to make sure it predicts the Q of this action one is 10,753 and the second action is 233? Since the only thing I care is that, action 2 is better and that's it. And training classifiers is easier than regressors. This is what your colleague is putting forward, right? Yeah, other comments? Yeah?
I think it might also possibly converge faster in the same way that policy iterations can converge to a policy faster than value iteration. Because you don't have to worry about the changes as long as the total ranking doesn't change.
Yeah, sure. This again goes back to the fact that training classifier is so much easier than a regression. And this is always the case. Training classifier is easier than a regressor, especially here that the values really don't matter. Yeah, so this is precisely also what they found. Guys, exactly what is the intuition that you're saying. So the first thing is that, look, Monte Carlo tree search planning discovers better actions than deep Q learning. That's it. This is what the first result here is. As you see, UCT has much higher score than the DQN baseline. All right. Now the second, and it takes a few days on a recent multi-core computer to play for each game in 2014. All right. So it's really, really slow, but it finds better Qs. The second conclusion is exactly what we just said, that classification is better than regression because we train exactly for what we care about. The only thing I care is what action to do. I don't really care about exact scalars of different actions, etc. Okay. I mean, same as you. In every scenario, you know what you need to do. You don't say, oh, if I do that, the score is going to be 753. And if I do, no, we don't think like this, right? We just care about which actions pop up in our head. And interleaving is very important to prevent this mismatch, this distribution shift between the states that the expert is going to visit, which is our Monte Carlo research planner, right? If you remember, we said that this guy just plays, runs of the game, etc., or instantiates itself to any state. So this state distribution better come close to the state distribution that our student, our agent is going to see when he's going to play the game. So this interleaving of, imitating the expert, deploying the agent in the environment, collecting new data, querying the expert for cues, imitating it, and repeat is very, very important to close that state distribution gap. Okay. And so this is very, very important. Results improve the more budget you give to Monte Carlo research planner. All right. So the more, the more time you spend, the more trajectories you allow to unfold, the more accurate are the cues. Now there is a limit to that, and they talk about this in the paper. I'm not sure how many of you had the opportunity to read it, but basically they say saving 6 divers brings a very high reward, but somehow exceeds the depth of our Monte Carlo research planner. And by the way, just to be clear, this game is not like Go. It's not like that there is a winner at the very end and no reward. So till then, playing Atari every now and then, the environment gives you rewards. If you eat the strawberry, if you kill the monster, if you avoid the fire, you all the time get positive and negative rewards. So basically, you decide the depth for your Monte Carlo research, for your random policy. So then you decide the maximum depth and you truncate there the trajectories. Is that clear? And then you say, depending on when you decide to truncate, you may never see that saving 6 divers actually will give you a really, really big reward, and your policy will never learn to actually save 6 divers. Okay. All right, perfect. So this is what I wanted to discuss on this paper. Are there any questions on this while we're switching to our next topic? Yes. Typically, no, because of the non-methodic exploration, basically, that we're also going to discuss when we talk about the intelligent exploration in our intelligent exploration lecture. Okay. Yeah.
Basically, I'm trying to question
How much DQN scales if we also give more compute and more CPUs and so on and so forth. Yeah. So the problem is the following: that these experience buffers have a specific capacity, and at some point you start, throwing away the old data and use new data as you keep trying and trying, and you don't have a stable way to remember what was the right thing to do in a particular state. Do you see? This is the problem, and sometimes you see the policy collapsing exactly because it reached a particular level, but now it forgot what it was supposed to do in the very early parts of the game. Do you see? So there is this problem. While with a Monte Carlo search plan, you have, you save those queues without interleaving. You don't have the problem that, I'm going to update the weights and I'm going to forget some earlier things that I had discovered and so on and so forth. And intelligent exploration, when we go to that lecture, is all about, can I safely save things that I have discovered that are good, some good trajectories, so I make sure I go back and imitate them, as opposed to, I found this awesome trajectory after exploring for so long, and now I dump it in my buffer, so now it's gone. It's just one good trajectory among all the other crap that I had, collected with my epsilon greedy exploration. Do you see what I mean? But this is a great, question. While the exploration here is much more methodic, right? Okay. And by the way, you need to understand that there is a huge period during trial and error learning. I mean, okay, Atari is easy because you do a little bit of thing, you get some tiny little coin, and you get some +1. So this is good. But there are many environments where to get your first non-zero reward, you need to jump the stairs, find the key, jump down, go in the tunnel, find the door, put the key in the door. There's so long sequence of actions that you need to get right completely by random exploration till you get your first non-zero reward, that such a trial and error learning is really, really, really hopeless. Do you see? That's the problem. And these are called the hard exploration games, and Montezuma's Revenge is one of them, and we'll discuss many, many ways how to get around that. All right? Okay. Other questions? Okay. But these are fantastic questions. Basically, we just put some very basic trial and error learning methods on the table, which we would need to combine both with imitation learning in the few lectures, as well as intelligent exploration, if we really want them to have agents that continually learn. Okay? Okay. Yeah. And I want to mention that research on model-based reinforcement learning is just booming, right? We have amazing papers coming out. We'll visit some fantastic papers from last year that have, answered open questions. But many open questions remain. For example, how do you learn models that really generalize to complicated environments and can transfer across environments and so on? But for today's lecture, we're just going to go back to standard trial and error learning. And we'll say that so far we focused our function approximation lecture, which was on Monday, was about deep Q networks, which how do we learn a good value function by exploring an environment. That's what we visited, correct? So today we are going to focus on some policy-based methods that through this exploration will directly be learning a policy. And this is kind of important, especially when the actions are continuous, because deep Q networks are only applicable when you have a finite, discrete finite set of actions to choose from, all right? And then at the end of today's lecture, maybe potentially coming Monday, we'll discuss about actor critic, methods where you jointly learn a value function as well as a policy, okay? Is that clear? So we have covered already value-based methods, and this lecture is about policy-based methods, and Monday we'll see actor critic methods. Okay, so let's discuss about policy optimization. At the end of the day, we were going to put down an objective that will be parameterized with the parameters theta of our policy, okay? And our goal would be to figure out how to update our policy parameters theta so that our objective improves. Okay? So basically, we'll initialize some policy parameters. We have some initial random policy. We'll deploy it and collect trajectories, and usually we'll use the Greek letter tau for denoting trajectories. Okay, so we'll denote trajectories, sequence action reward, sequence of state action rewards by deploying a current policy in the environment, and we will be updating our policy. Then we will use the new policy to collect new trajectories and see their returns, which is the sum of rewards of their states in the trajectories, update our policy, deploy again, and so on and so forth. So this is the form of iteration that we'll be using in this lecture. Is that clear? This is very similar to what we saw with DQN, where instead of initializing randomly the parameters of our policy network, we're initializing randomly the parameters of our Q network. That's all. Now, from the Q through epsilon greedy, you would come up with a policy, you'll deploy the policy in the environment, collect trajectories, and so on and so forth. Do you agree? Okay. Okay. Now, interestingly, you may say, well, this is just an optimization problem. We may as well try some very simple grid search methods or evolutionary search and so on. And you would be absolutely right. In fact, one of you asked me this question 2-3 lectures ago. And we will compare policy gradients, the particular method that we'll visit in this course, to evolutionary methods for optimizing the parameters of our policy. Okay, in a later lecture, in like 2-3 lectures from now. Okay. And why we discuss about alternative, black box optimization methods? Well, for the following reason: the U theta, the objective that we're trying to optimize, will not be differentiable with respect to the parameters of our policy. Do you see? So we have essentially a non-differentiable optimization problem that we need to solve. All right. And you know what? When you're confronted with a non-differentiable optimization problem, you may as well try some genetic algorithm methods or some, standard black box searches. And my question for you, well, first of all, let me put down the objective, and then I'll ask you why, if this is differentiable or not, and so on. Okay. Yeah. So we will be talking about this policy gradient, but you will see that essentially is not an end-to-end differentiable problem. We'll come up, though, with this vector that you will, have to add to the current parameter set of your policy to essentially hope that your policy improves. And the policy functions that we'll visit will have the following forms. Either if we have continuous actions and we have a deterministic policy, then we have our policy will be a neural network that takes the sensory input and have some parameters and spits out directly the action, which means what? The coordinates of the gripper, the steering angle, and the brake of the car, etc., etc. Directly, it will spit out directly the essentially the parameters of your action. Is that clear? Like, for example, the steering angle. If you have again continuous actions, but your policy you want to be stochastic, typically we'll be using a Gaussian. Okay, so essentially the output of your network will not be directly the steering angle, but will be a Gaussian with some mean and variance, out of which you can sample those steering angles. And a big part of our lectures will be coming up with good architectures that can handle such stochastic outputs. All right, the Gaussian is the most naive way to essentially parameterize such stochastic continuous policies. All right, so we'll come up with more interesting architectures and parameterizations of the output layer there. And the more simple one that we've already seen is I have a policy over discrete actions, and that policy is still stochastic. And I'll have a softmax layer, and again the input comes in, and then I have my network, my parametric function, and then I have an output layer that converts logits of different actions to a probability distribution over them, and then I just sample an action from there. Is that clear? Now, the important thing to understand is that when we have stochastic policies, we will be sampling an action, all right? Because the neural network will just parameterize the distribution a Gaussian distribution in case of continuous actions and a categorical distribution in case of discrete actions, while in deterministic policies, the neural network directly parameterizes the action. There's no distribution, okay? It's just a deterministic mapping. Is this clear? Okay. Yeah. So today's lecture will be on stochastic policies, both on discrete actions and continuous actions. For optimizing deterministic policies, we will see it actually in 2-3 lectures from now. Okay? So let's come up with a policy objective. What we would be happy to optimize for our policy to optimize. Just before start, intuitively, I would be happy if we could optimize something that essentially takes into account the rewards of the trajectories that our agents collected by navigating the environment. Okay. So to do that, first we need to, define the trajectory tau, which is a state action sequence, and state action and reward actually. Then we can define the return of a trajectory, which is the sum of instantaneous rewards at every time step. And of course, most of the time steps, the reward will be 0 when you have sparse reward environments. And a reasonable policy objective in this case would be an expectation under trajectory sampled from our policy of the returns of those trajectories. Okay? How do you feel about this? So our policy, how does it enter into this objective u theta? Well, our policy enters in that objective u theta because it's used to sample those trajectories. Okay. Now, once you sample a trajectory, then you look at the rewards and the environment assigned in individual states, and you sum them and you say, okay, these are the returns of the trajectory, and here is my u theta. This is how good my policy is right now. Is that clear? Okay. Does anybody remember to tell us what is the probability of a trajectory? Probability of tau that depends on theta? So let's assume that for now the trajectory is essentially it's a sequence of state actions, state actions, state actions. Yes?
It's just a big product of the probability of each of those actions in the trajectory.
Yeah. Okay, that's right. Well, it is a big product of the probability of the individual actions on the trajectory, right? But let me try to explain. Yes, I agree. But the environment also enters into that probability. Okay, you may do an action, may try to open a door. In an environment, the door may be closed or open with some probability. If it's open, then something is going to happen. And if it's closed, something else is going to happen in the future time step of the trajectory. So along with the big product of those individual actions and their probability, what other else we need to multiply?
The probabilities of the state transition.
Yeah, of the transitions of each ST, each individual state and time step T to the next state, ST plus 1 condition on the action that we took. Do you remember that, guys? Let me show it one more time. So H is the horizon of the trajectory, the number of time steps of the trajectory. So exactly like your colleague said, we have a long product of the probabilities of the individual actions, which we know, and the probability of the transitions of the environment, which we do not know in this lecture. All right? We knew it in some old time, before Monte Carlo and TD and so on, we knew those transition probabilities. Is that clear? Okay. So then I suppose we're all about the gradient descent. We need to compute the gradient of that u theta with respect to our parameter theta. Okay. Yeah. Now the problem is this end-to-end differentiable? Is this objective end-to-end differentiable? This is what we need to understand. Is there essentially a function, okay, there's an analytic function, it can be differentiated, that links the parameters of our policy theta to the u's, to essentially the returns of trajectories. The same way that in an image classifier, when I try an image classifier, there is a nice and analytic function, right? This classifier that links the parameters theta to the entropy loss. all right? So then I can backpropagate on the entropy loss and update my parameters theta. This is what exactly I'm asking. Yes?
Your policy is differentiable, then yes.
If your policy is differentiable, then yes. Okay.
Yeah.
So that's now the most important thing for all of us to understand. So let's assume our policy is differentiable, because actually all policies we'll see in this course will be, the input will be the state or the set of images, whatever, and the output will be what? The probability distribution over actions of the present time step, correct?
Right.
Okay, so let's assume that this function is differentiable. Now this unfortunately links the input image or the sensor input in general to the actions that you're about to sample, and there's no loss over those actions. Can somebody, I want to ask you, if we were doing imitation learning and somebody would give you ground truth actions, would my policy be end-to-end differentiable or no? Does anybody want to raise his hand and say why no or why yes? Okay.
We have the ground truth actions, then it's like a classification problem.
Uh-huh. Uh-huh. Yeah, great. So now I have my thetas, the link to actions, I have the ground truth actions, I can put the max entropy loss there. If I have discrete actions, or I can put regression loss if I have continuous, and then I will do gradient descent. Okay. Now this is not our setup though. This is we're not in an imitation learning setup. Nobody supervises our actions. How we're going to get how good or bad our actions are? What are we going to do? Well, yes, but we need to deploy this policy in the environment. That's what I'm trying to say. You have your mapping, you have some random thetas that they map your sensor input to your actions. Now you need to take your agent, sample actions from that policy, and deploy it in the environment, either in the real environment or a simulation environment. And then you will get back what? Trajectories. And the environment is going to spit for you rewards at random time steps of those trajectories whenever something good or bad happens. And then you can look at those rewards, okay? And then we said, now you need to update your parameters theta to maximize the rewards of those trajectories. Is this now this end-to-end differentiable? This is the question. Yes?
You don't know the dynamics, and you're not learning the dynamics also. And would you not know whether any individual action was good, or if it just happened to put you in the right state?
Yeah, exactly. So we don't have the dynamics at this lecture, all right? So the only thing I have is my policy, and then I need to deploy to this unknown environment, and then basically do some random things, and then somebody tells me, oh, plus 100. It's like, oh, plus 100, something good happened. I have no clue which one was good of the 15 things I did, but one of them was good. Do you see? And now I need to use now this external reward signal to figure out how I'm going to update my actions. We have some fantastic, there's an amazing blog post and also corresponding slides about learning ping pong from pixels with reinforcement learning that you really, really need to read. Okay, it's a part of your required readings. Okay, but this is very important for all of us to get right. But don't worry, the lecture, yes.
Where does it break down in the math world? It seems like this objective is differentiable, right, with respect to theta. I mean, you just take the log of that product, then you'll have terms corresponding to the environment dynamics, which doesn't depend on your policy.
Yes.
You have the term corresponding to your policy.
Yeah.
Which is differentiable.
Yeah, but we're not trying to maximize the probabilities of trajectories. We don't have a maximum likelihood problem here. We're trying to maximize the returns of the trajectories. So let's go through the math exactly what you said. Do you see? I'm not trying to make those trajectories just more likely, because some of them are bad. In fact, I really don't want to make them more likely. So let's see how exactly this will happen. Okay, policy objective. So here is again, it seems we're all happy with this objective. Okay, so now we need to compute the gradients. And in general, when we want to compute derivatives of expectations with respect to the variables that parameterize the distribution where the random variable is sampled, and not the quantity inside the expectation, meaning the reward does not depend directly on theta. This is the case where we're in. So the assumption is that this is a probability density function that is continuous and differentiable, and P is also easy to sample from. which is indeed is the case. This is our policy. So let's see how this is going to happen in the general case. We have a derivative of an expectation where, our items X are sampled from some distribution that's parameterized with parameters theta. And, we get these X's, and then we have f of X, which is exactly what we're trying to maximize. Is that clear? So we just started from our specific objective, and then we said the general form, the general formulation is precisely that. So here is the derivative, and let's assume that this expectation is a large sum, very, very big sum over items X multiplied, and inside the sum we have how good each item X is, which is the trajectory at the f of X. The reward of a trajectory is essentially that f of X, and the probability of that X, the probability of that trajectory. Okay, so this is the big summation. So we can push the gradient inside that sum, and why we can do that? Yeah.
It's a linear operator.
Yes, it is a linear operator, and you can push the gradient inside exactly. Exactly. And the problem is that now we're stuck. This is the problem here, guys. We are a bit stuck here. What is the problem? The problem is I have a homologous sum, and I have this huge sum, and every item of that sum is comprised of the gradient with respect to theta of p theta of X multiplied with some scalar, f of X. So f of X is like the reward of the trajectory. And the question is, what is gradient of theta of p theta of X? The p theta of X is essentially the product of the actions in the trajectory. And we know how to take the derivative of our policy network because our policy is differentiable. And I'll give you the precise, let's say, form of those gradients in like 2-3 slides from now. All right. So by the way, we'll see the derivation of the math also with our actions. So I'm not sure what to do here. That's the problem. This is a huge sum. I do not know how to approximate it, but here's what we're going to do. We're going to multiply and divide with the probability of those x's. Okay, that's all. We haven't approximated anything. Still, it's the equality sign. And I want to ask you, what is the gradient with respect to theta of p theta of X divided by p theta of X from the chain rule? Yeah?
The gradient of the log.
Yeah, the gradient of the log. Do you all agree with so far with our derivation? Yes.
Here are you assuming that f of x is not dependent on theta?
Say it one more time.
Here are you assuming that f of x is not dependent?
Yes, f of x is not dependent on theta. If f of x was also dependent on theta, then you would need to also differentiate it. Okay, we are saying, guys, here that the probability of a trajectory depends on our theta because we said it's a product of the individual actions, but the reward of that trajectory does not depend on theta, on our policy. Given there is a trajectory, then the environment will give a reward, and that's it. This is just scalar. All right? All right, so why we like the last line more than the third line? First of all, do we all recognize what is our last line? We have a big sum over items X, and each term on the sum is multiplied with the probability of that X. So what do we have here? An expectation. All right, is the expectation with respect to X is sampled from that p theta of X of the grad theta log p theta of X multiplied with f theta. Okay. And so what is the big thing that we achieved? What is the big thing we achieved? We know how to approximate expectations, right? We will just sample. So we know how to form approximation of this line, while we didn't know how to form an approximation of the third line. In both cases, we have a homologous sum, right? But the last case, this sum has the form of an expectation, which essentially, I can obtain now an unbalanced estimator for that grad theta of epsilon x fx, exactly what I was looking for by sampling. And, you know, from the law of large numbers, if I sample, you know, long enough, then I will actually get a very good estimator. So this is the hope. Is this clear? Okay, let's repeat exactly the same thing, but now we're going to be using our own terminology. We're trying to maximize that U theta, which is the expectation over trajectories sampled from some probability of trajectories, which we know what it is. It's a product of the action of the individual actions, as well as some dynamics that really don't depend on theta, okay, of the reward of those trajectories. So by doing exactly the same thing, I will just, you know, write down the expectation in terms of the big sum. I have my gradient, so the derivative is a linear operator, so I'll push it inside the sum. And I have a homogeneous sum of the gradient of theta, the probability of a trajectory, multiplied with the reward of the trajectory. Now, the reward of a trajectory, is it a scalar or a vector? A scalar. It's a scalar. And now we will see how simple it is to just compute the gradient theta of that theta of tau based on what your colleague has said already. And actually, this is also what your other colleague pointed out, that sure, we can differentiate this. So we have a long product of the probabilities of individual actions as well as the probability of the individual transitions. And in front of it, we have the current with respect to theta. And so things are looking good here already because the transitions actually do not depend on your policy. The environment and the world is what it is. No matter what you do, it doesn't depend on your policy. Okay. So this is great because now all the dynamics, which we really do not know, but it's just a constant, so we don't care. And now we have the gradient with respect to theta of essentially the long product of actions. All right, that's pretty much it. And you know, this little log product of actions, this is a differentiable policy, so we know how to compute it. Is that clear? Okay, so we know. So this is totally under control. Yeah, and it's a long vector, right? How long? As many as the parameters of our policy. That's how long it is. So we don't have any problem with the blue, but we have a huge problem with this big summation that we don't know how to approximate. So who would like to tell us what we're going to do now based on what we did in the previous slide? Multiply by 1. Why should we multiply by 1?
P theta tau over P theta tau, and then do the same log approximation.
Right. So you're saying we're going to divide and multiply, right, with the p theta of a trajectory. Exactly what you said. Now the grad theta p theta of tau is the grad theta log, right, with the chain rule of the derivatives. And now we have an expectation under trajectory tau sampled from our policy, essentially, of the grad theta log p theta tau r tau. That's it. And this is called the policy gradient. Okay? And of course, we do not know that expectation, but we can approximate it with sampling, right? So we are not scared of expectations because we know how to approximate them. So we will take our current policy, deploy it in the environment, get a bunch of trajectories tau, and form that summation. Okay. All right. So let's go back and see how this is. So the other beautiful thing here is this logarithm. So this, you know, p theta of tau was a very long product, but now with the logs going to become a sum. So let's go and take a look exactly how this is going to look like, because our tau of I, everybody knows how to compute. You take your trajectory tau, sum the rewards that you saw on that trajectory, and this is precisely your return of that trajectory tau of I, right? So is this 100, like crystal clear how to compute it? Okay, so then let's see how to compute the red term. Let's go back here. So grad theta of the log of that long product, and now the log of the product is a sum of the logs, and of course the dynamics don't depend on theta. So the only thing that's left is the grad theta of the sum of the log of the probabilities of individual actions. Yes?
Does the previous slide assume that no trajectory has a 0 probability?
Right. So if a trajectory has 0 probability, it's not going to show up on your set, right? It's not going to be sampled. No, there is no such assumption. Like, it's just an expectation. If a 0 probability, that trajectory will not count on that expectation because it has 0 probability.
I mean in the step where we divide by the probability.
Oh, I mean, it doesn't matter. It doesn't matter because in any case it cancels, right? So we can just hang it around there. In any case, it cancels. All right. So I don't think this matters. All right. Okay. So is this 100% clear? Okay. All right. So now you know exactly what your vector is. So basically, the grad theta u theta, which is this blue thing, grad theta log the probability of each trajectory, is essentially a summation over individual time steps of the grad theta of the log of your policy. So to compute that, you really need to take your policy, which will be your, the neural net with the softmax or the neural net with the Gaussian parameterization, right? Either your policy will either parameterize a categorical distribution or a Gaussian distribution, and really take the derivative of the log of your policy. And we'll see exactly what this is. Any questions so far? Yes.
Can you explain again why this form is easier than whatever we had previously?
Yes, how the derivation, why we did this multiplication and division with p theta of tau. This is what you're asking.
Why this is like preferable over whatever we had?
Right. So let's see. When you say whatever we had, I think maybe you mean here.
Yeah.
Right. Because now I do not know what to do here. Because I need to compute an approximation on my grad theta u theta. Okay. I have some very long vector with my current parameters of the policy, and I need to compute that gradient. Okay. To add it to my current theta with some learning rate and come up with a better new theta vector. Correct? So now the problem here is I have this big summation over all possible trajectories. Each one of those vectors, grad theta, p theta of tau, multiplied with the returns. Correct?
I see.
And then what are we going to do with that? We need to approximate it. Right.
Is the problem here that we're trying to enumerate?
Yeah, it's an intractable sum. Exactly. It's just it's just too many. It's like an integral. I make it a sum because they're just more approachable than integrals. But yes, exactly what you said.
Yeah, I see.
Mm-hmm.
Thanks.
Yes.
So like back to the problem of like not knowing whether your actions are good for the environment or because it's a good action.
Uh-huh.
The reason why this works is that that's because you're taking the gradient as an expectation over many trajectories, whereas taking the gradient of an individual trajectory.
Very good question. Excellent question. We'll go back to this in a few slides. But the idea is that, yes, you have no clue in one trajectory what was good, what was bad. But because you sample tons of trajectories and, maybe you learn correlation. Oh, when I do this action, I get plus 100. Maybe this is good. Do you see? That's the reasoning behind this. Absolutely. But we will see this in very good slides in a tiny bit. Okay, great. So now, so we'll call this G hat, which is going to be the approximate gradient vector. Sounds great. So let's see. So now, guys, you know everything. You know how to compute this grad theta u theta by taking your current policy, deploying it in the environment, getting a batch of trajectories, capital N, each one with some, horizon, capital T. You compute the rewards of your trajectories, you form these vectors, and you're done. Then you have a new vector, and you add it on your current theta, and you come up with a better policy and so on. So that's how policy gradients work. So to be able to carry this out, we need to be super concrete of what this red part is. What is this red term? So let's see. We said that our policy network will have two forms. We will either parameterize a Gaussian or a categorical distribution. So let's start with a Gaussian. How this grad theta log p theta of alpha will look like, okay? Let's assume, usually, when we have a continuous actions and we use the Gaussian parameterization to sample from, we assume that the variance is fixed, and our neural network parameters only parameterize the mean of that Gaussian. All right, this is a wild simplification, but that's what we do. Okay, we will see other things as well. We'll see other network where you also parameterize either diagonal variances or some full covariance metrics. Okay, so we'll see a lot of those. But for now, let's assume that it's a fixed variance. So for a univariate Gaussian, if your action has only one coordinate, let's say the steering angle, the speed is always the same. You also don't brake, you just steer. So then the Gaussian will look something like this. And how the grad theta of the log could look like, who would like to tell us? Who wants to take the derivative of this? Sigma and the 1 over sigma square root 2 pi does not depend on your policy. Okay, sigma we said is fixed, so forget about this. You only need to worry about the exponent. So let's take the log of this. So what's going to happen? The log of and the exponent are going to cancel each other out, correct? Do you agree? Okay. So now the only thing you need to do is take the grad of theta of the exponent. So what will this be? We have a square in the exponent. Who would like to walk us through with computing the logarithm and the gradient of that very simple univariate Gaussian? Then does anybody want to raise his? Yes, please. Okay, yes. So we have this thing, right? We have two terms, 1 over blah, and the other is the exponent. So if we take the log of that, so the log of a product is what?
Some of the logs.
Exactly. So we have one log of something that really doesn't depend on theta, and you don't worry about take a derivative, so you don't worry about that. And then you have the log of the exponent. So the log of the exponent is what?
The exponent.
The exponent, perfect. So now the only thing we have is the exponent. So what you are ready to do now, take the gradient of that.
Yep.
Great. So take the gradient of that, the inside the exponent. So what's going to be?
I'm going to ignore the sigma too.
Sure, because only the mu depends on theta. Okay, and then?
So chain rule, so the square will come out. So I'll get negative a minus mu times negative mu.
The gradient of mu, because mu depends on theta, we said that our neural network will parameterize that mean, correct? Perfect. Great. That's it, guys. So standard chain rule, there's nothing mystic. The problem is with these PyTorch packages, nobody now anymore computes derivatives. That's the problem. You see what I mean? So the thing is that we need to remember, it's very simple. So what does this mean? This means I have a neural network that parameterizes a mu. So the changes, theta change, the mean vector changes. That's all this means. Okay. And I want to change my theta so that my mean goes towards the action, let's say. That's what this says. Now, this is going to multiply it with the reward of the trajectory. So just remember that. If the reward is positive, I want to go towards this action. If the reward is negative, I want to go far away. Okay. All right, great. So for the multivariate Gaussian now, we have more than one coordinate for our action, steering angle, how much to brake, and so on. So I have a vector. That's fine. So what comes out of my network is a mean vector that has as many numbers as my action coordinates. And essentially, if you take the grad of the log of this, it looks something like that. Now, the good thing is that my thetas do not parameterize this covariance matrix for this slide. So you don't need to worry about this. That's why it's just constant. And then you have essentially this, A minus mu, and the theta of the different mu's will split the theta of the different theta coordinates, okay? You take every mean with respect to every of those parameters. Now, the next slide, we will do something very, very simple. We'll say, what if there is no thetas, and directly I parameterize these means? I have two parameters. Imagine that I am in a two-dimensional plane, okay, and I have some two-dimensional Gaussian, and my parameters are these mu1, mu2. The mean, the two mean values of my mean vector, okay? The two coordinates of my mean of the mean of the Gaussian. So this is how it's going to look like. So then I don't need to worry about the theta mu theta theta anymore, right? The gradient of the mu with respect to theta, because I parameterize directly my mean vector. So essentially, what does this mean? What is the intuition of that? Well, you have a policy, all right, which means a specific mu1, mu2. You sample actions from that two-dimensional Gaussian, and here is how they look like. They look like dots because they are two-dimensional. And then you compute the rewards of those guys. Some are +1, some are -1. And then you fit them on that essentially here. We have this A minus mu, exactly what we said. So this we don't need to worry about this identity. We have forgotten this f of x of I. F of x of I is essentially how good is every action. Do you see? So some actions are +1 and some are -1. So what do I want to do? I want to move my mean to the actions that have +1 to make them more probable, and far away from the actions that have -1 to make them less probable. That's all that happens. Okay. So now here is my updated mean. I went a little bit down to make those green actions more probable and the red ones less probable. Is that clear? That's all this policy gradient vector does. And just for completeness, I just want to tell you that we just saw the Gaussian parameterization. This is the categorical parameterization. This is how the softmax layer looks like. So your neural network will take whatever input, have tons of layers, and at the very top is going to have some logits. For every action, it's going to have a scalar. So what you're going to do in the softmax layer is you raise that on the exponents and then divide with the sum. So now you convert those logits to a probability distribution over those actions. Correct? Great. So now, again, with this different policy network, you need to go and compute, so the output is distribution over a discrete set of actions. And now let's go and for that policy network, compute the grad theta of log p theta of alpha, how it's going to look like. Well, in this case, the p theta of alpha looks like that. Okay, sure. Well, we need to take a log and then we need to take the gradient of that. So things now are a little bit more complicated. Because the first thing we need to remember is that the log of a fraction is the log of the top minus the log of the bottom, okay? And the log of the top is essentially the log and the e and the exponent cancel one another, and that's why you see only the h there. Are you cool so far? All right. All right. So now that's all. Now we're going to take the log of the sum. Okay, there's nothing we can do there, I suppose. What happened now? Okay, so the grad theta of the log is 1 over what's inside the log and the derivative of the inside, right? This is from the chain rule of the logarithm. So that's why the logarithm disappeared. And then if you continue doing now we push the derivative inside the sum because the derivative is a linear function. And let's continue a little bit more. Nothing special is going on here. Well, okay, we took the gradient of the exponent, which essentially is, if you remember the chain rule for the exponent is the same exponent and the derivative of what's inside the exponent for those that remember the rules of derivative, and so on and so forth. And that's how it ends up being, okay? That's all. So this is actually what's happening, what will happen in your PyTorch, let's say, script, if you take the derivative of that policy. And you know what? These h's are exactly the logits. Here is this essentially is the back propagation. All the derivative will spell all the layers of your network are inside this grad theta of h right there. Okay? So now you know everything. There is one thing I want to discuss more that your colleague had mentioned, which is as follows. Let's go back to our g hat, which is this gradient, the policy gradient. Well, if you see how this looks like, is that we have a big summation over the different actions that we saw in our trajectories. in any of the capital N trajectories, in any of the capital T time steps. And for each one of them, we have that vector grad theta log p theta of alpha. If you follow that vector, you make that action more probable. But in front of that gradient, we multiply with the goodness of how good every action is, all right? And how good every action is, we said that it depends on the reward of its trajectory. So you do a bunch of stuff, then you get a reward, then you try to do credit assignment. Who is responsible throughout my horizon for the good or the bad reward that I got? Now, if the reward, if we're not unlucky and the reward doesn't come always on the final time step, but rather is sprinkled throughout the different time steps, there's something better we can do, which is instead of just assigning the sum of rewards to all the actions, I better assign, if I'm the third action, I should compute my goodness based on the rewards that come after me, not what happens before me. Do you see? This is something extremely intuitive. So, and that's all. That's all this temporal structure says, that we need to split the sum of rewards to what happens before I occurred as an action and what happens after I occurred. So I want to be multiplied only with all the actions that happen after me. So we have this updated formula, okay? So every action takes the blame for the trajectory that comes after its occurrence. Any questions? Okay. So we can call this return from G onwards. Usually we call it GT, if you remember. That's how we used in Monte Carlo lecture. All right, so this is our likelihood ratio gradient estimator. So now we have a particular parameter theta for our policy, and the new theta will be the old theta plus alpha, and GT, which is the reward of a particular time step, grad theta divided by theta, which is the grad theta log theta essentially. Okay. All right. Which means what? The first one, it says move in the direction that will favor an action that yields high return. And the bottom one is, well, divide with the probability of an action so that so actions that are more probable do not take an advantage. That's why we'll divide the probability of an action. So this is how we intuitively understand that return multiply with the grad theta log theta, okay? So, and here we are ready to see our first policy gradient method, which we'll call reinforce. It came out in 1992. You initialize your parameters randomly. You sample trajectories tau by deploying the current policy. You form the gradient, grad theta u theta, exactly what we just discussed, with depending on if your p theta is a, parameterize a discrete policy or a continuous policy, whether parameterize a categorical distribution and Gaussian distribution. You update your theta, and you go back to, collect your trajectory from the environment and so on and so forth. Okay? So that's it. So now we have a complete pseudocode, and you're going to get the opportunity of implementing this or something a little bit more advanced of this in the homework too. And now we'll go to the most fun part of the lecture. Okay? Pong from pixels. So what is Pong from pixels? Imagine that you're controlling one of those two, panels, and your goal is to hit the ball. So if you hit the ball, things look good. And if you miss the ball, you get a negative reward, all right? So this is what happens. So you start a game, and then you play. And if you lose, then you get a negative reward. And if you win, then you get a positive reward. You have only two actions. Either you can go up or you can go down. And you can get +1 if you pass your opponent and -1 if your opponent passes you. And that's all. Correct? That's all. So given that we have two actions, which policy parameterization do you think we should use? Our policy network, how should it look like? Yes? A regression. Okay. A regression, you mean to spit out the mean vector?
Sorry.
What regression you mean?
rather than classifying up or down, you could just give like the probability of going up and the alternative is going down.
Okay, but this is precisely the definition of a classification network. That's precise, right? Is a network that in the output layer gives you a distribution over a set of discrete choices, right? So it's a classifier. Now, if you have continuous actions, then you cannot use a classifier. You need to have a network, another network that parameterizes the mean of that Gaussian distribution for where we're going to sample. Okay, but here that we have discrete actions, it's only two. I say we just use a classifier, which means what? We need a softmax layer. We'll spit out two logits or one logit because the other will be one minus, or maybe two, and then put the softmax, and that's pretty much it. Okay, and this is how it looks like. And specifically because it's two, you can just, the only thing you care about is the probability of one action, because the probability of theirs will be one minus the first. Yes.
Can't you frame it as a regression problem if you frame your action space in that way, like hold down the down button for like t seconds, so you could have a regression over the time you press down a certain action. So if you press down the action for 2 seconds, the down button for 2 seconds will go down for that duration of time, right? So your action space could be.
Yes, I agree. But the thing is the following: in MDP, this is what we say: we have discrete time steps, and you need to interact with the action in a particular way, and then you get rewards.
Discretize it in a way that first a state can represent like a shorter duration of time. So if it's representing like discrete, like if you're discretizing it as like 1 second steps, I understand, but like if you discretize in a different way.
Yeah, so maybe I think what we're trying to say is, what if I have an action space that instead of being the individual actions is the actions over t time steps? Yeah, you can only get worse in this way, though. There's no benefit from doing that, right? Because you are working on a coarser time scale, especially in our Pong game, right? You will not see the fine grain, oh, I got this reward right at this particular time step, and so on and so forth. I don't see a benefit of anything in that non-intuitive, let's say, discretization of time. Okay, yes.
Yeah, why we are not using DQN in this case? Because I have two actions, so I can estimate QSA, right?
Right. Yes, you can also do that. The only thing is that what we hope to do with those slides is to give an explanation of what's behind the policy gradient. And the good thing with policy gradient is you can also use it for continuous actions, while DQN is not being used, right? Do you see? But this is excellent point, okay? DQN are used all the time for playing Atari games, exactly because it's a discrete action set. All right. Now, the first thing you need to decide if your policy is a classifier or a regressor, okay? What will be your output parameterization of your actions? Once you decide that, then you also need to decide what the rest of the architecture is going to be. So does anybody have suggestions here? So because you don't care to train something that actually is going to do well, this, here Andrei says, let's just take the whole image and flatten it. All right, and then you put the big MLP, and then you're done. That's it. Now we're talking about 1.3 million parameters that need to be estimating, because that's how many weights need to touch every pixel. Okay, now here is now the big illusion, right? The grand illusion. So you guys see this beautiful thing with the two panels and the ball, and the network sees nothing. The network just sees a bunch of numbers. It doesn't know what's a ball. It doesn't know what's at the table. It doesn't know that the same thing actually moves up and down. It doesn't have idea of permanence. It just has numbers, that many, one for every pixel that it sees at every time step, and that many numbers because these images are binary, right? Black and white. They are not 3 RGB. And now the idea is that you play, you get plus and minus rewards, and how I need to assign now 1.3 million parameters. That's the question. So it's playing, the poor thing. Now, suppose we had the training labels. Suppose we have an expert that will tell us, in this state, you need to go up. In that state, you need to go down, and so on. What a beautiful setup. Your colleague said earlier, then it's just maximal likelihood problem. It's very easy, okay? I can just train, and everything is end-to-end differentiable, and we don't need to talk about policy gradients and so on. But this is not actually what happens. This is the case of supervised learning. And we need to maximize the probability of the actual actions given the state, and you're done. And you've done this already in Intro to ML. But the problem is we do not have the labels. And what is the idea of reinforcement learning? It's super simple. Try a bunch of stuff, see what happens, do more of the stuff that worked in the future. That's all. This is trial and error learning. It's extremely dumb. That's why it's so sample efficient. So what does it mean, try a bunch of stuff? It means take your current parameters theta, randomly initialized, play, and then you're like, oh, I won. Great. And here I lost. And then I won, I lost. That's it. Bunch of numbers, and then win, lose, win, lose. And then you're like, I don't have a clue what happened, but it was good. And here I'm not sure exactly what happened, but it was bad. Okay? That's all the algorithm knows. And then it says, now pretend that every action we took in the wrong trajectory had the negative label, and pretend that every action we had in the positive trajectory had the positive label. Okay? And this +1 and -1 is what? The returns of the trajectories, essentially. And essentially, and this is where essentially these R's are those -1s and +1s. And that's pretty much it. Now the gradients actually match. You have exactly the same gradients that you have in supervised learning, but they're essentially pre-multiplied with this advantage. Okay? It's the same. The log of the probability of a particular action, this is exactly the grad log, okay? But it's the pre-multiplied with those advantages. And I'm going to let you go, is 110. Come here, we have office hours if you have any questions. Read the amazing blog post. Yeah, and the other, of course, chapter 13, I think, from the book, and hope to see you on Monday. Thank you.